This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 13, the Schrodinger Equation. The Schrodinger Equation governs the evolution of the entire universe. H psi is equal to IH bar times delta psi over delta t. H is the Hamiltonian operator. The physical meaning of H is the total energy of the system. Psi is the wave function of the system. I is the square root of -1. H bar is h over 2 pi. H is the Planck constant. So H bar is roughly 10 to the power of -34 joule second. This is how psi changes with time. For a one-dimensional particle, psi is equal to psi of x and t. The wave function of the one-dimensional particle depends on its position and time. The Hamiltonian of this one-dimensional particle is the sum of the kinetic energy operator and potential energy operator. Again, this negative h bar squared over 2m times delta squared over delta x squared is the kinetic energy operator. Later, we'll apply this operator to the wave function psi. And this, again, is the potential energy operator that may depend on the position of the particle and time. So this is the Schrodinger equation for the one-dimensional particle. H psi is equal to kinetic energy operator plus potential energy operator being applied to psi is equal to IH bar times delta psi over delta t. And we can separate these two operators. We basically apply the kinetic energy operator to psi, the potential energy operator to psi separately. The result should be IH bar times delta psi over delta t. This is very complicated, but we can simplify this if the potential energy does not really depend on time. And then this V of x and t is just V of x. In this case, we can often separate the position x from time t. By setting this equation, we assume the wave function is a product of this lowercase psi of the position times another function of time. And this function of time is e to the power of -I et over h bar. I is the square root of -1. E is the total energy of the system. T is time. H bar is the reduced Planck constant. By doing so, we can plug in this expression of the wave function here. And then here. Over here, the function of time is this exponential function. And now we apply this delta over delta t operator to the wave function over here. Because this lowercase psi is independent of time, in this case, we treat this lowercase psi as a constant. We take this psi out of delta over delta t. We just need to evaluate the first derivative of this exponential function. It is this. All right, we used a calculus rule, chain rule. So e to the power of t is the first derivative of e to the power of t is simply e to the power of t. The first derivative of e to the power of a constant times t is that constant times e to the power of that constant times t. So I'm putting that constant right here. Now we combine I and -I, that's 1. We delete this h bar and this h bar. In the end, we see this expression is simply E times psi times F. Now the Schrodinger equation for the one-dimensional particle becomes this. On the left-hand side, you have kinetic energy being applied to the wave function. Potential energy being applied to the wave function. On the right-hand side, this is actually from this IH bar times delta psi over delta t. Now you can see Ft ft can be cancelled. Now we have this equation. In this equation, we have the kinetic energy operator being applied to this lowercase side of the position. Potential energy being applied to the lowercase side of the position. On the right-hand side, it's the energy of the particle times the wave function of the position. Simply put, we have H psi is equal to E psi. H, again, is the Hamiltonian, but in this case, we say H is time independent. H does not depend on time. It's the sum of the kinetic energy and potential energy. In psi, this lowercase psi is said to be an eigenfunction of this H. So what does this mean, eigenfunction? If you apply this operator to one of its eigenfunctions, the result will be the same eigenfunction multiplied by a constant. So we are applying this H to this psi. The result is psi times a constant. Therefore, we say psi is an eigenfunction of H, and this E is the corresponding eigenvalue. I'll give you a few examples. Sine 2x is not an eigenfunction of d over dx operator, because when we apply this operator to this function, we get a different function. If you look at the result, we cannot say the result is sine 2x multiplied by a constant. Let's look at the second example. Sine 2x is an eigenfunction of the second derivative of operator. Why? If we apply the second derivative operator to this sine 2x, what's the result? Well, what you need to do is you need to take the first derivative twice. The first time you will get 2 times cosine 2x. And then you take the first derivative of 2 times cosine 2x. That's going to be negative 4 times sine 2x. Right? So now we can tell that this sine 2x is indeed an eigenfunction of the second derivative operator, and negative 4 is the corresponding eigenvalue. Similarly, you can prove that cosine 2x is also an eigenfunction of the second derivative operator, and the eigenvalue is also negative 4. Now let's look at this H. This H is a linear operator, so if both f and g are eigenfunctions of H, and then the linear combinations of A, F, and G are also the eigenfunctions of H. Let me give you a specific example. Again, if F and G are eigenfunctions of H, then if we apply this H to this linear combination, the result is 4 times H being applied to F plus 5 times H being applied to G. Assuming, again, fx is an eigenfunction of H, the eigenvalue is A, and assuming this G is also an eigenfunction of H with the same eigenvalue A, and then we have this result. The result is A times the linear combination of F and G. Now let's look at one more specific example. 4 times cosine 2x plus 5 cosine 2x is also an eigenfunction of the second derivative operator. Negative 4 is the eigenvalue. So we can do this. We apply the operator. This is second derivative operator to the linear combination of sine 2x and cosine 2x. You go through these steps. The result is going to be negative 4 multiplied by this same linear combination. Therefore, we say this linear combination is also an eigenfunction of the second derivative of this operator. Second derivative operator. Now I'll give you this question. Is this linear combination of sine 2x and cosine 2x also an eigenfunction of the second derivative operator? The answer is yes, and the eigenvalue is -4. Now, same linear combination, different operator. The answer is no. If you apply this first derivative operator to this linear combination of sine 2x and cosine 2x, you will not be able to get this linear combination in the result. Now, we learned this is operator, this is also operator, and there are some other operators. A number can become operator, so this is operator. If we apply this operator to a function, the result is 2 times that function. 0 can be operator. If we apply the 0 operator to a function, the result is 0. A function x can be operator. If we apply this x operator to a function, the result is x times the function. 5x squared can be an operator. When we apply this 5x squared operator to a function, the result is simply 5x squared multiplied by that function. Sin y can be an operator. Sin y operator being applied to this fx is sin y times fx. Now let's look at a more complex three-dimensional particle. We need x, y, and z in the wave function, and we need 3 terms in the kinetic energy expression because the particle may move in the x direction, y direction, and z direction. The wave function, again, is a function of 4 variables now: x, y, z, and time. The potential energy may depend on x, y, z, and time as well. And this is the right-hand side of the Schrodinger equation. But again, if the potential energy does not change with time, somehow we can separate time from the spatial coordinates. By setting this equation, we assume the wave function is the lowercase side that depends only on x, y, and z times a function of time. And this function of time is, again, e to the power of -I et over h bar. E is the square root of -1. E is the total energy. T is time. H bar is the reduced Planck constant. And then we put this into the Schrodinger equation. We get this equation here that includes ft in every single term. So we cancel all those f of t. We get the time-independent Schrodinger equation for a 3-dimensional particle. Again, over here we are looking at the sum of the kinetic energies in the x, y, and z direction. This is the potential energy, assuming it does not change with time. And this is the total energy. Simply put, h psi is equal to E psi, and this h is a time-independent Hamiltonian. This part is the kinetic energy operator. This is the potential energy operator. The sum of the kinetic energy operator and potential energy operator is this h. So over here. And this equation is the so-called time-independent Schrodinger equation. What if we have many particles? Well, then we need to include their positions, x1, y1, z1 for particle 1, x2, y2, z2 for particle 2, and in the end, this wave function does depend on time. Now we need to have to sum up all the kinetic energy for all these m particles. The potential energy depends on the positions of all particles and time, and then h psi is equal to IH bar times delta psi over delta t. Again, if the potential energy does not depend on time, we can simplify the time-dependent Schrodinger equation to time-independent Schrodinger equation. In this case, h is again the sum of the kinetic energy operator and the potential energy operator. So be sure you understand that there are 2 general Schrodinger equations. One is the so-called time-dependent Schrodinger equation, in which this h and psi both depend on time. So there's a typo here. It should be uppercase psi. There's also a time independent Schrodinger equation. So this h psi equals e psi is the time independent Schrodinger equation. This psi, this energy, and this h are independent of time. Now let's look at some complex numbers, complex functions. It's a quick review. I is defined to be the square root of -1. So I squared is simply -1. I cubed is I squared times I. Therefore, it's just -I. I to the power 4 is simply 1. I to the power 5 is I to the power 4 times I. Therefore, it's going to be I. And you can easily determine I to the power 6, -1. I to the power 7, -I. I to the power 8 is 1. You can also calculate, some simple product of two complex numbers, 1 plus I times 1 minus I. We get 4 terms here. The result is 2. 1 plus I times 1 plus I. Again, we get 4 terms. We simplify those. We get 2I. This is because I times I is -1. -1 and 1 cancel. Now, A plus BI times A minus BI, well, the result is simply A squared. So this is actually A plus BI times A minus BI, in which A and B are both 1. All right? Oh, I'm sorry. There's a mistake here. This should be A squared plus B squared. All right? So A times A is A squared. BI times negative BI is actually positive B squared, because plus times minus, you get minus, but I squared is also -1. You have two negative signs, and they cancel. A plus BI times A plus BI is A squared minus B squared plus 2ABI. All right, now let's look at a interesting equation here. A complex number or function, A plus BI, can always be expressed as this. A plus BI can always be expressed as R times cosine theta plus I times sine theta, and sine theta plus I sine theta is e to the power of I theta. We'll prove this part later, but now first let's think about this. A plus BI is equal to R times cosine theta plus I sine theta. How can that be possible? The thing is, on the left-hand side, we have two independent variables. On the right-hand side, we also have two independent variables, R and theta. So as long as we define A to be R cosine theta and B to be R sine theta, we have this equation, right? And by looking at these two equations, we realize R is the square root of A squared plus B squared. So basically, you just square this equation, you square this equation, and you sum it up. You get A squared plus B squared is equal to R squared cosine theta squared plus R squared sine theta squared. And cosine theta squared plus sine theta squared is just 1. How do we define theta? Theta can be defined as just B over A, right? So B over A is sine theta over cosine theta. And then you have to determine this theta by looking at the values of B and A and also the signs of B and A. If both A and B are positive, theta is between 0 and 90 degrees. If A is negative, B is positive. That's between 90 and 180 degrees. All right, so again, you need to imagine a, let's say, XY axis, all right? XY axis that separates the two-dimensional space into 4 quadrants. So if both X and Y are positive, you are in the first quadrant, all right? Theta is between 0 and 90 degrees, right? In the second quadrant, X is negative, theta is between 90 and 180. In the third quadrant, both X and Y are negative, theta is between 180 and 270. In the fourth quadrant, you have positive X and negative Y, theta is between 270 and 360 degrees. Now let's prove this equation. E to the power of I theta is equal to cosine theta plus I sine theta. I think this is Euler's equation. We'll prove this using the Maclaurin expansion of this function, and this function. So let's look at the general expression of the Maclaurin series. Fx is f0 plus, over here, something times x, over here something times x squared, something times x to the power of 3. So any function, any smooth function, can be expanded into a polynomial function. What about the coefficient? The coefficient is 1 over here. This is 1 factorial, 1 over 2 factorial, 1 over 3 factorial, etc. What about this one? Well, you just need to take the first derivative of f and then plug in x equals 0. The second derivative, and then plug in x equals 0. You take the third derivative of the function and then plug in x equals 0. So this is the simplified expression. It's just the sum of 1 over n factorial. Over here, this is the nth derivative of the function, and we plug in x equals 0 in here to get a number, and this number times 1 over n factorial. This whole thing is the coefficient in front of x to the power of n. Now let me give you 3 examples. Cosine theta, we can expand cosine theta this way. And over here, this is the nth derivative of cosine theta. The first derivative is, of course, negative sine theta. The second derivative is negative cosine theta. Right? And then sine theta, cosine theta, negative sine theta, negative cosine theta, etc., etc. Remember, if we look at sine theta and plug in theta equals 0, sine 0 is 0, cosine 0 is 1. So that's why we get this series. All those sine theta terms disappear. We have just 1 minus theta squared over 2 factorial plus theta to the power of 4 over 4 factorial, etc. Similarly, we can deal with sine theta. We can expand sine theta. What's the first derivative of sine theta? It's just cosine theta. What's the second derivative of this? Well, it's simple. It's negative sine theta. Right? And the third derivative is negative cosine theta, and then sine theta, cosine theta, negative sine theta, so etc., etc. What about the first term? The first term, that means we are not taking the derivative at all. So it's going to be d0 over here over d theta 0. It's just 1. So the first term is actually 1 over 0 factorial times theta to the power of 0. 0 factorial is 1. So that's why we have just, just 1 times... I'm sorry. I think I made a mistake here. When n is 0, this entire thing should be just 0. Okay, so when n is 0, you are looking at d0 here. D to the power of 0 is 1. This is also 1. So we're looking at just sine theta. Alright, it's just sine theta. Sine 0 is 0. Therefore, we do not have the first term. The second term is 1 over 1 factorial times, well, over here, this is the first derivative of sine theta. That's cosine theta. And cosine 0 is 1. So we have 1 over 1 times theta to the power of 1. So that's this term. All right, and we have some other terms. You can easily verify the other terms. Now we have cosine theta and sine theta determined here and here. Now e to the power of I theta, similarly we can expand this. Similarly, we evaluate the derivatives of e to the power of I theta. It's right here, e to the power of I theta. We can take its nth derivative. The result is I to the power of n times e to the power of I theta. And then we plug in theta equals 0 here. We get this result. And now we plug in n equals 0, 1, 2, 3, 4, 5, 6, 7, etc. And now we can see some terms contain the imaginary number I some terms do not contain I, so we put all the real parts together and the imaginary parts together. Now you can see this part is simply the Maclaurin expansion of cosine theta. This is the Maclaurin expansion of sine theta. We just proved e to the power of sine theta is cosine theta plus I sine theta, and e to the power of negative I theta is simply cosine theta minus I sine theta. Now we can also write out cosine theta and sine theta in terms of e to the power of I theta and e to the power of negative I theta. Because if you sum up this two, you get 2 cosine theta. If you use this minus this expression minus this expression, you'll get 2I sine theta. And therefore, we can also get the expression of cosine theta and sine theta in terms of e to the power of I theta and e to the power of negative I theta.